Greetings, students. Welcome to your first lecture of physical chemistry. It's my hope that by doing these pre-recorded lectures, you'll be able to go back and study and maybe make some better use of the class time. We'll try it out and we'll see how it works. As you can see here, we are starting off with quantum mechanics. And that's because I believe that quantum mechanics is really important. It's essentially the foundations of chemistry. And by starting off with quantum mechanics rather than with thermodynamics, we can better understand, thermodynamics when we get there. So what we'll start with today is we're going to try to understand how quantum mechanics developed. And so to do that, we'll be going through the first 4 sections of chapter 12. And the question we're going to try to address today is, why do we study quantum mechanics? And so I'm hoping that by addressing this question now, it will help to motivate us as we go through the semester. And I'm going to tell you right now that the reason we're studying quantum mechanics is not just because the chemistry department here at Hillsdale and at other universities have decided that we have to torture you guys with this topic. And there's actually much more that goes into quantum mechanics. And in fact, it is very, like I said earlier, it's very foundational. And you can't really do chemistry without a good understanding of quantum mechanics. So we'll start again. We're going to be addressing this question. So why are you here? I know for some of you, I kind of convinced you to take this class, but for others, what are you actually doing in this class? So why are we learning quantum mechanics? So the first thing that I want to bring up is, of course, that quantum mechanics describes how matter works on a microscopic scale. Now, this is going to be important because atoms are, of course, on a microscopic scale. So as chemists or biochemists or potential doctors, right, we're trying to understand how these concepts work. So how do atoms get together and react? And looking at large bulk properties is helpful, but when it comes down to it, if we really want to know how 2 atoms are going to interact, we need to know quantum mechanics, how very small things work together. And it turns out that there are many techniques that are based off of quantum mechanics. So things, for example, like lasers, like even a common laser pointer is based off of quantum mechanics. And you can go into more, fancy things like integrated circuits, maybe you've heard of quantum computing, and so forth. But on a more fundamental level, why are you here in this? Why is this a chemistry class? Is that most of our modern chemical knowledge is based on quantum mechanics. So these include things like orbitals, so both atomic orbitals and molecular orbitals, things like bond angles, and even spectroscopy. So I wanted to go through a little, thought experiment here, and maybe it's not quite a thought experiment, but I want to have you guys just imagine, go back to organic chemistry and picture an IR spectrum of your unknown molecule you were trying to figure out in an organic chemistry lab. And what you're going to see there is some sort of peak. So let's imagine your molecule has a carbonyl. Maybe you see a peak like this. Maybe you actually had 2-butene on this molecule here. And we learn in organic chemistry that we can identify this. So we have a carbonyl stretch over here. We have a CH stretch over here. And these regions of this IR spectrum tell us what molecule we have. But let's stop and take a step back and think about what's going on here. So in this molecule, we have this big, strong, skinny peak at 1715 wave numbers, and we memorize in organic chemistry. This is a CO stretch. It's a carbonyl stretch or peak here. What does that mean? Well, that means that our carbonyl in this molecule is absorbing light at 1715 wave numbers. We'll talk about wave numbers more in the future. They're just a convenient way of representing energy. So this carbonyl is absorbing light of a certain energy. What is it not doing? Well, it's not absorbing light at 1725, 1735, 2991, right? It's absorbing only light in this very specific region. And another way to say that is that the kinds of light that this carbonyl can absorb are quantized. We can count them. Can only absorb a certain amount of energy and not others. Now, this might seem obvious to us as 21st century chemistry students, but this is not at all obvious in terms of having quantized energy. Before the advent of quantum mechanics, everyone thought energy is continuous, and in fact, that is the common experience of people. So, for example, if we think about a sport like baseball, that baseball that the pitcher throws can have any energy, it can have any speed that the pitcher throws it at. It's not quantized. It's not limited to being 95 miles an hour or 90 miles an hour with nowhere in between. But when we get down to the quantum mechanical level, these very small particles, it turns out that energy is in fact quantized. And that has really important implications, as we can see in this spectrum here. And we only get certain absorptions for each kind of bond, and that can be, that's crucial, in fact, in determining what molecule we have. And the last thing, of course, we have to note here is that this is going to be a pretty hard class. And one of the main goals of this class is to develop your problem-solving skills. So mostly this class might end up seeming like calculus word problems. And that's essentially what it's going to be. So we'll start by looking at some of the tenets here of quantum mechanics that and kind of how they don't really fit into a modern classical physics. So like I said earlier, this can seem, some of these things will seem very obvious to us. Like we'll go through on the next lecture, we'll talk about wave particle duality, and you guys are like, yeah, of course, that's how it works. I learned that already. But I want to try to put us back into the shoes of these 19th and 20th century physicists who were involved in discovering quantum mechanics. Because as obvious as this stuff might seem, because you've been told it so many times, it is actually very, very weird. And so we'll start off by looking at experiments that were kind of the thorns in the sides of classical physicists. Classical physics were not able to explain them, and that's where the development of quantum mechanics comes in. And so we'll start today by, we'll start every lecture, hopefully, by these learning goals, and these are the things that I want you guys to take away. So hopefully these learning goals will serve as a nice sort of sheet of study sheets for exam. So if we come up to the exam and say, I can do all of the learning goals and all of the slides, I should be in a pretty good place to do the exam. And so our learning goals for this lecture will be to describe the limits of classical physics, and these will kind of bleed into the next lecture as well. And we're going to compare the quantum mechanical model and the classical models for the experiments that we explore today. And one of those will be the photoelectric effect, and I expect you to be able to do some problem solving using the photoelectric effect. And you should be relatively familiar with this from Gen Chem. So, like I mentioned, we're going to start by picturing where classical physics is at the turn of the 20th century, so like 1890, 1900 sort of times. And this is going to be pretty interesting to explore, where these guys are coming from. So at the turn of the 20th century, we had a lot of pretty big scientific discoveries that were going on. So, for example, a few hundred years before this, we have Isaac Newton, and Isaac Newton, as we all know from physics, he has done a lot of great work that has helped us understand, how the world works. So he has the 3 laws of motion, right? We have Isaac Newton's, first, second, and third law. He has the law of gravity, which describes not only why things fall, but how the planets move in the solar system. And he also discovered calculus, and we can use calculus as a very helpful tool for us to figure out, how these things are, how the world works. We can explain it mathematically. After that, we also have, in terms of chemistry, we have Dmitry Mendeleev. So this is pretty contemporary with the turn of the 20th century, about 30, 40 years before. He comes up with the first versions of the periodic table, and is finally, and not just him, but the chemistry as a whole, is finally figuring out, what an element is. So why is oxygen oxygen and not hydrogen or helium or something like that? And then about in 1873, we have James Clerk Maxwell, and you may be familiar with him. He uses, he coins Maxwell's laws, and these laws show how electricity and magnetism work together. and explain these two very weird things, right? Like magnets are super weird if you think about it. And he is able to explain them with physics. And so with these three men and observations like theirs, the attitude in the early 20th century, late 19th century was pretty much that us humans are capable of fully understanding everything that there is, right? We're smart. We either know now, and if we don't know it, we're going to figure it out in 10, 15 years, and we'll know everything about how physics works. Now, this today might seem kind of laughable to you because, as we'll see, quantum mechanics kind of throws a thorn in the side of these ideas. And so what we can do now is we're going to look at some of these experiments that these classical physicists knew and we didn't quite know the answers to. And so the first two here we're going to go over today, we'll save the second two for next time, is the idea of black body radiation. And then we're going to talk about the photoelectric effect. We'll save the double slit diffraction and the hydrogen emission spectrum for Friday. Before we get too far into these experiments, I want to kind of get a broader picture of where we're going to go. So we're going to start here by looking at these first, problems. Why do we need quantum mechanics in the first place? And then after that, we're going to actually start to apply some quantum mechanics. So starting next week, we'll look at Schrodinger's wave equation, which gives a mathematical framework for quantum mechanics. Basically, everything we do in this class will be based off of this wave equation. And in order to do this, we do need to be somewhat familiar with some higher level math. In my opinion, and in interacting with students over the past couple of years, this math is not beyond the level of your average, calculus knowing college student. So I will post some math review videos that I prepared before if you guys want to review. So some of the math that we're going to need for this class includes, very basic calculus, so doing things like integrating and taking derivatives of exponentials and polynomials, and some trig functions, anything harder than that, and we'll just kind of skip over it. So no integration by parts in this class. Maybe you're happy with that. And then other sorts of things you'll want to be familiar with are how differential equations work, as well as the ideas behind imaginary numbers. And then for later in the semester, we're going to want to use matrix mathematics as well. So having a good grasp on these math techniques is going to help us understand what's going on here, because a lot of quantum mechanics essentially is, well, we did the math and it gave us this weird answer, and this weird answer is consistent with the experimental results. So being able to do the math there is going to help us out. If you have any questions about math, please, come talk to me about it sooner rather than later. Okay. So the first problem that we're going to discuss is also the first problem sort of in chronological order of its solution, and that is the problem of black body radiation. So there's a lot of sort of like hard to understand things going on here. So like, what do I mean when I say black body radiation? And essentially what I mean, so one example of black body radiation is hot coals. So you add heat to charcoal and it glows, it emits light. And that's essentially what's going on here with black body radiation. So heating up things causes them to emit light, and what kind of light does it cause them to emit, and can we understand that? That's the questions that we're going through here. So what happens when you add heat to ideal black bodies is they emit many wavelengths of light. So we emit some heat, and that's like IR radiation, things that are coming off as heat. And then also some lights here. So you can see these coals are emitting heat when we have them to a temperature, and they also emit red light, maybe some yellow light, maybe some orange light, and so forth. So what scientists were trying to do is saying, can we describe exactly what's going on here? And so they did their best to construct an ideal black body. Here we have a kind of schematic of an ideal black body. And this is ideal because it allows the light to bounce around inside and come out only of this small aperture and reach equilibrium as it does so. And so they could use, doing this, they could use classical electromagnetic theory, right? So James Maxwell, very good at describing magnetism and electricity. And we could use that theory to describe what's going on and what kind of light do we expect to be emitted. And so I'm going to go into some detail here, but don't try to get too much in the nitty gritty, because it's really hard for us to put ourselves in the mind of a 19th century physicist. And that's not quite what we want to do. But they're asking what frequencies of light are emitted from these ideal black bodies. And the answer that classical electromagnetism got them is the following. So according to classical electromagnetism, the energy of oscillation is equal to kT. We'll use this a lot here in this semester and also more next semester. But kT is kind of our placeholder for the energy that comes from temperature. So K is the Boltzmann's constant, which is 1 over the gas constant that you're going to be very familiar with. And it has the units of joules per Kelvin. So if you multiply that by temperature, you get an energy. So the idea here is that you have some sort of temperature that's supplying some amount of energy to your molecules or your system. And using this, using the fact that the energy of our oscillations in the coal molecules or the metal molecules or whatever is our black body, the spectral density here, this is the wavelengths of light that are going to be emitted, or the frequencies rather, should be equal to this following expression. So it should be 8 pi kT over the speed of light cubed times the frequency squared. So I went through all this, like gave you this math, and you're sitting there and you're saying, okay, that's great. Of course, that's what the spectral density is equal to. But let's take a step back and think again about what this is saying. So our left side of the equation here, our spectral density, is talking about what kind of wavelengths of light, the energies associated with those wavelengths, would be emitted. And this is dependent on, these are all constants here, it's dependent on the frequency squared. And so what that means for us is that as the frequency increases, as we get to higher energy light, they are going to be emitted more from ideal black bodies. So what this predicts then is that regardless of the temperature, as long as the temperature is not absolute zero, we will get increasing amounts of light emitted as the frequency increases. And so what this is saying is that according to classical physics, we would predict an infinite amount of light, an infinite amount of energy to be emitted from black bodies at any temperature. Now, you'll probably understand that this is, of course, not possible. We can't have an infinite amount of energy come from a finite amount of energy. And that is, of course, true. And so this, you may have heard this before, that this is going to be coined as the ultraviolet catastrophe. And here, the reason this is called an ultraviolet catastrophe is because the energy is equal to the area under the curve. So this dashed line here is the predicted, the theoretical amount of light emitted, and that has an infinite area under the curve, so it has an infinite amount of energy. And that, of course, is not true. Rather, what's the way that these black bodies work is according to these red curves here. So this is a relatively easy experiment to do. You could heat up a black body to a certain temperature, measure the emitted wavelengths. But the problem was that we didn't have a theory to explain this. So why do the curves look like this? So to solve this problem, again, classical physics is not quite working. We have German physicist Max Planck in about 1900. And he has a critical observation here. So what we're going to do is going to look at the 6,000 Kelvin curve and the 3,000 Kelvin curve. And what he notices is that if we go here, let's say we go out to our 8 times 10 to the 14th frequency, there's nothing coming out of the 3,000 Kelvin one. So this relatively low temperature is not emitting any light with frequencies of 8 times 10 to the 14th. However, our high temperature one is emitting quite a bit of light at that frequency. And so what he's noticing here is that the high temperature light is the only light, or the high temperature black body, sorry, is the only black body that's capable of emitting these high frequency lights. And of course, that is not captured in our original theory here. And so what he does then is he proposes that, well, the energy that's coming off, right, might not actually be dependent on the intensity. And we'll look more about this in the next slide. But maybe that the energy is actually dependent on the frequency of the light. And so if we have higher energies at 6,000 Kelvin, we get access to higher frequency light. Again, this relationship between frequency and energy might seem obvious to us as 21st century chemistry students, but it is not at all obvious to a 19th century physicist. The other supposition that he makes is that perhaps the oscillations are quantized in some way, and this quantized, which just means quanta, means we can count them. They're not continuous; they're discrete. Again, this is a very strange thing to propose. But when he proposes it, he gets the following. So he gets that this energy here, rather than being equal to kT, is in fact equal to h nu, which he's saying is the energy of light. Again, remember, this is a controversial idea at the time. And then we divide that by e raised to the h nu over kT minus 1. So what does this get us? Give me a second here, and I'll bring this up on my iPad so I can do a little bit of writing. So here, again, we're looking at this expression, E is equal to h nu over e to the h nu over kT minus 1. And so we're going to look at a couple of different scenarios here. The first scenario is going to be, what if our h nu is much, much greater than kT? So in this scenario, what happens is that we have our gap in our energy, so the energy needed to excite this transition, it's much greater than the thermal energy that's available. Well, in this case, h nu is a large number and kT is a small number. So this is going to be a large positive number. And we can say that as this gets larger, this is going to end up towards going to infinity here. So what will happen then, if we plug this into our equation, h nu over e to the infinity minus 1 is essentially h nu over infinity, over a large number. So this goes to 0. So if our h nu is sufficiently large, we can't actually excite those transitions. So we don't get these high energy emissions for h nu that's much larger than our thermal energy, our kT. What about the other scenario? What if we have, in fact, that we have kT is much, much greater than h nu? Well, in this case, we're going to have h nu over e to the small number, so we can say approximately 0, because this will be our h nu over kT now will go to 0 rather than infinity, minus 1. And this gives us kind of a weird thing, because we'll say, well, e to this 0 is 1 minus 1, we don't have an answer. But what we can do is use the following simplification here. So if we have e to the x, where x is a very small number, this is approximately equal to 1 plus x. So we have this substitution we can do in here. And if you don't believe me, go ahead and check this out on your calculator. So what this is going to give us then is h nu over x. In this case, x is h nu over kT. And then we have plus 1, and then we have our minus 1 from our equation here. So this will simplify to 1 over kT, or kT. This is a really important thing that we do here, and we're comparing our quantum mechanical predictions to our classical models. And we find out that in certain limits, so in this case, in the high energy limit, we get the same explanation. So these two things, this math that Planck does, explains why we have high frequency emissions only for high temperatures, and also why for low frequency emissions, where kT will be much greater than h nu, why that actually fits pretty well with the experimental model. Let's go back to the slides now. So again, here we can see our high frequency emissions are only at high temperatures, and for low frequencies, it actually fits the pretty inaccurate model reasonably well. So when Planck takes these suppositions and he gets this expression for the energy of oscillation, he plugs that in and he gets this following expression here. Remember, this is our old expression that didn't work, and this is the new expression that Planck gets. And what he finds is actually that it matches the experimental data perfectly. This it is not quite enough information. So he gets the perfect experimental match, but people were still pretty skeptical. So what this seems like, and maybe you can agree with this, is that Planck just kind of came in here with some weird suppositions. He made up some quantization. He said the energy is dependent on the frequency and not the intensity. He made up some weird stuff, and sure, it got him the right answer, but he's pretty off the wall here. None of this stuff that he actually said makes any sense, and it can't be real. And then we'll look at two other experiments that kind of show that, you know, maybe Planck was onto something here. And you probably suspect that Planck was onto something because you know his name and he's got a constant named after him. And that is, of course, this H constant here. This will be one of our best friends in quantum mechanics. So the next thing that we'll look at is going to be the photoelectric effect. And you might remember the photoelectric effect from Gen Chem. Essentially, this effect says that when you shine light onto metal surfaces, that light is capable of kicking electrons out of these metal surfaces. Now, this is one that hopefully you remember to understand from Gen Chem, or maybe we'll refresh it pretty quickly here. But this experiment clashes very hard with the ideas of classical physics. So classical physics predicts for us two things. One, that light is a wave, and two, that the energy is dependent on intensity. So what this would say is that when we're shining this light wave on the metal surface, this light wave has energy. The energy is split up sort of in the same way that the energy of an ocean wave is all across the beach that it's clashing on. So the energy is divided equally among everywhere that this wave hits on the metal surface. And that the energy is dependent on intensity. And what we mean by intensity is brightness. So the brighter the light is, the more intense it is. And so what classical physics would predict then is that if you have more intense light, right, the brighter the light is, the more energy is being absorbed by the sheet, and the faster the electrons that are kicked out should be kicked out. Now, this is not observed at all. The observations are totally different than these classical predictions. So the first thing is that the high intensity light does not cause electrons to be emitted faster. It causes, in fact, more electrons to be emitted. So if you shine a brighter light, the electrons are emitted with the same speed, but more of them come out, which is very strange. Second, it turns out that the emission is dependent on the frequency of light. So if you change the frequency, it changes the color of light. So now if you shine blue light instead of red light, now all of a sudden the electrons are coming out faster. And probably the most freaky thing of all here is that very low intensity light still emits electrons as long as it is of a high enough frequency. So say we have blue light. Blue light is capable of emitting electrons. We dim that way, way, way down. And we can go, infinitely down so that the energy of the light wave is the energy that is needed to emit one electron. The light wave hits over the whole surface of the metal, and one electron comes out with the same speed that it always does. And this is clashing again with this idea of light as a wave that had been demonstrated for centuries at this point. And we could describe this mathematically. So the kinetic energy of the emitted electrons is depending on some constant, we're calling this beta for now, times the frequency, and then minus this other constant phi that's metal dependent. And so this phi is something that's kind of holding the electrons to the metal. We know now that's the attraction with the nucleus. You give it enough light, if you have more energy than what's holding it down, it's going to come out. The more energy you give it, the faster it's going to go. And again, a pretty strange result. Now, Einstein solved this problem, and this is actually what Einstein's Nobel Prize comes from. It's for solving the photoelectric effect, not relativity. And his solution, again, seems pretty common today, but it's a very shocking and maybe disturbing idea here, is that we have wave-particle duality. So light waves also act as particles. So he is calling, Einstein, we know, calls light waves groups of photons. And this explains sort of the whole thing we have here. So Einstein says that these photons are coming out when we increase the intensity. We're actually increasing the number of photons. That gives, more brightness, more intensity, but not any more energy. And so we get more number of electrons emitted rather than more intense, more fast electrons. And then the last thing here is that when Einstein fits the data, we can see we can fit this data nice to a line, and the slope of this line, this beta constant here, is in fact the same constant that Planck used, this H constant. So that shows us that we have these two very different experiments that give the same constant, and maybe what we have is actually a fundamental constant of the universe, which of course we use it today as. So we'll continue with this next time. So now we have these ideas of quantization of energy and wave-particle duality that Planck and Einstein proposed, and we'll use those next time to describe the remaining two experiments that we have.